we'll go ahead and get started. We're going to do more resonance today because you can never do enough resonance. And then what we'll do is on Wednesday, we're going to start. We're going to start module 2, which is, if I'm not mistaken, acidity and pKa. We're going to start that. That's a cool section too. So I'll send the videos out for that later on this afternoon. I got a packed schedule this afternoon, but I'll send it out. And then I have my schedule set in my phone. I have on my to-do list for Thursday for our recitation at 6. Just use the class link. So it's in my phone and we're going to just work it from there. All right, let's go to, let's go to here. We're going to work 2 examples out of here. All this is asking is to supply the arrows. So before you can supply arrows, what do you need to identify?
The acceptor and the donor.
Donor and acceptor. Thank you. You cannot do resonance without a donor and an acceptor adjacent to one another. So in this case, right, in A, for A, we have a pi system right here. And remember, the pi system can be a donor or an acceptor, but bonded to it, we have a anion, right? So this is going to follow the same or similar type of pattern to the allylic anion, right? So this is going to be my donor. This is going to be my acceptor. And if you look over here, it gives you the other structure. So it's just a matter of putting the arrows in and show how you got to that structure, right? So if you notice over here, I have a pi bond here now, right? I'm missing, I broke a pi bond here, and I have a new lone pair. Get a thinner pen. I have a new lone pair here on nitrogen and a charge. Right. So what arrows would you put in? And feel free to annotate if you're able. You have that capability. You can annotate your screen and put the arrows in, and just show what will happen. And let me stress this: even if we don't do every problem on resonance, my suggestion is to work through as many of them as you can. If you get stuck, ask questions, because I just finished my 9 o'clock class, which is part 2, full of students who should know resonance, and yeah, it's not there. So please, please, please make every effort to master this. Like, I promise you, because you never get away from it. You're always going to see it. Anybody want to annotate that? Put the arrows in. If you're on a computer, you should see on your toolbar a little function that says annotate. It's going to be clumsy if you're not using a stylus, but you have to use your mouse pad or mouse. But it is what it is. We'll take it however we can get it. Or if not, you can tell me what to do.
Can I just say it?
Yeah, come on.
So you would take the lone pair over the CH and put the arrow to that single bond, and then that'll make that a double bond.
Right here. Hold up.
Yes.
Come on, iPad. Here, right?
Mm-hmm.
And then what else? Because if we don't do anything else, that carbon that's triple bonded to nitrogen is going to have 5 bonds to it, and that won't fly. Is that right?
Mm-hmm. And then so you take that triple bond and put the arrow to the nitrogen, and it'll make another lone pair on top.
So we good, excellent. So we take one of those pi bonds and break it and give it to nitrogen, and that's how we get to that second structure. Excellent. All right. Now let's go to C. Any questions about A?
I have a quick question. Can you explain again how you can determine which one is the donor and acceptor, especially for that one?
Good question. Good question. Okay. So a donor can be a lone pair or a pi bond. An acceptor can be a pi bond or a cation. If you have to choose between a lone pair and a pi bond as a donor, always choose the lone pair, if that makes sense. Right, see here we have both scenarios, right? We had a lone pair on carbon with a negative charge, right? If it's an anion, it's definitely going to be a donor because that atom is trying to get rid of that charge however it can, and resonance is one way to do that, right? So that carbon we identified as the donor because it was a lone pair and it was charged. That made the pi bond next to it by default the acceptor. But if you are stuck between the two and you have a lone pair that's adjacent to a pi bond, choose the lone pair as your donor.
Okay, thank you.
Great question. All right, let's do C.
Can you hear me?
Yes.
So a lone pair is considered an atom without a double bond or anything next to it. It's just
Well, it could.
negative.
So, yeah, it could. So that would be an anion. But if you notice right here, you got a lone pair on nitrogen also, right? The problem is you don't have an acceptor for that lone pair. So you wouldn't push that lone pair in resonance towards that carbon, because otherwise that carbon is going to have 5 bonds to it, right? But if you look on the other side where that anion is, that lone pair on that carbon is in a position to be a donor and the carbon is the acceptor. Does that make sense? Like the nitrogen is, even though it has a lone pair, if you let me put it this way, the lone pair on nitrogen is not aligned with the orbitals in the pi bond, so it can't donate. That's the technical reason why we don't use that one. But the carbon next to it, the anion, that p orbital where those electrons are is going to be lined up with the p orbitals in that pi system. Is that clear or no? That's a great question.
Bit.
Yeah, that's a great question. So normally when you have a lone pair like that on a nitrogen, like a nitrile, that's what that functional group is, a nitrile. That lone pair is perpendicular to everything. So the p orbitals are like, if we had to think about this in terms of what the orbitals look like, the p orbitals would be here. They'd be coming up here like that, and then here. And then that lone pair on nitrogen would be pointed the opposite direction. It would be here. So if it's not aligned, it can't overlap. And if it can't overlap, it can't share electrons. Right. Remember that was when we first started talking about this, I showed you a system that had 3 p orbitals. It was an allylic system that had p orbitals overlapping. And that's how the electrons get shared when the orbitals overlap. But if it's perpendicular like that, it can't overlap, if that makes sense. And they have to be the orbitals. And I know some people frown on, making this kind of giving characteristics to inanimate objects, but if the orbitals can't talk to each other, then they can't share electrons. And so if it's perpendicular out of the plane, it can't talk to the ones that are in the plane. Hopefully that clarified that. All right, let's do C. We got another example right here, same, it's a similar example, right? It's going to follow that pattern of an allylic anion. Right, we have a pi system here, and bonded to that pi system, you have a carbanion. There is a negative charge there. I just added in some electrons, but let me use a smaller pencil so the electrons won't look so goofy. So there's a pair of electrons there. So which one of those do you think is going to be your donor? And which one is the acceptor?
Over CH.
Yep. Now here's another example right here. You got lone pairs on oxygen, even though they're not shown, they are there, but they're not donors, right? The anion is going to be a better donor than those lone pairs for a couple of reasons. One is that they're outside the plane, right? They are kind of bent, where your p orbitals on the carbonyl would be, if you were looking at this on a flat surface, they'd be coming up out of the page. So that's the first issue, is that those orbitals don't overlap, but these do overlap right here. So these orbitals are going to overlap with the p orbitals here, right? So you're able to, those three atoms are able to talk, able to overlap orbitals, share electrons, and because of that, you can do resonance. So let's look at the other structure. Other structure is over here, and you can see where the double bond is, where the new double bond is that right? And you see now oxygen has a negative charge, and that's because it picked up another lone pair. So what are the arrows going to look like in this case to get us from the structure on the left to the structure on the right?
You're gonna draw an arrow from the lone pair with the CH to the left, yeah, right there. And
Yeah,
then
okay,
the
good.
double bond under the oxygen, you're gonna draw one of them up to the oxygen.
Good. Excellent. That's exactly right. Now, this is only one of the resonance forms, right? Because you could do the same thing in the other direction. Is that right? Because you have another donor acceptor pattern right here, don't you? So you could also do that resonance form as well, but you can do that one on your own as practice. But if you, how do I put this? If you have multiple acceptors, then you can always do more than one resonance form. And in this case, you have two acceptors and a donor and one donor. All right, so you're going to get at least two resonance forms. All right, any questions? Anything that goes over your head, stop. That's the best way to grasp the information, and it's also the best way to keep yourself from falling into a hole, so that when you get to part 2, I got to reteach part 1. So let's not fall into a hole. Ask all the questions you want. It doesn't matter.
For C, how would we know when there's lone pairs that aren't shown?
Well, in this case, the carbon had a negative charge on it. And so that's indicative of the fact that there's a lone pair on that carbon. Anytime I give an exam, though, I don't use this method of not showing the lone pairs. But for some reason, and I know what the reason is. Some book authors feel like at this level, you should already have mastered Lewis structures. And so that's why they don't put them in. But I always put them in. So, but if the carbon has a negative charge, it has a lone pair on it.
Thank you.
Great question. All right, let's go to 141 and look at the question. We're going to talk about this because resonance and stability go hand in hand. Right, the more resonance forms you can draw, the more stable the particular molecule in question is. So it says for each pair of ions, determine which ion is more stable and use resonance forms to explain your answer. All right, so let's do D. Right? Let's start with the other side, and this is a cation, by the way. And we haven't talked about this, but this is a great time to talk about this. So I'm going to put it over here. Oh, maybe we did talk about it. Did we talk about primary, secondary, tertiary, and methyl? Did we talk about that the other day, one day last week? I think we did. That's okay. We can do it now. This is a great segue to that topic. So we have 4 types of cations that we're going to talk about. So the first type is a methyl, right? The second is a primary. I'm just gonna write it like this. Primary, you'll see indicated with a 1 degree. So 1 degree, whenever you see that in relation to a carbon, that means it's a primary carbon. All right, so that's primary, and then we can have secondary. And then tertiary. For some reason, I feel like we talked about this already. At least we talked about,
We went over it in our notes.
right? We talked about the bond order, you know, primary, secondary. Well, I don't think we talked about it in relation to cations and anions. So it's a good place to do it. So for this is all these are different types of carbocations: methyl, primary, secondary, and tertiary. So here, the carbocations increase in stability as you add groups around it. So the methyl in this case is the least stable of all of your carbocations. I'm gonna change colors right quick because I should have put this on a separate page. Should I? What do y'all think? Yes, no?
Please do a separate page.
Yes.
Okay, all right, let me do that. Because I can give some other information that I want to talk about too. So, and I hate squeezing stuff in there like that. When I go back and look at the notes, I'm always appalled. Like, God, you should have put that on a different page. All right, I can even make this bigger too. So methyl, primary, secondary, tertiary, carbocations, the stability is increasing in this direction. Right. So this is a trend that holds up no matter what. All right. So the methyl is the least stable out of all of your carbocations. And the tertiary is the most stable. Right? It's the opposite for anions. So for carbanions, methyl.
We can't
Dr.
see
Russell?
the screen.
Really? Stop.
We only
stop
see your
sharing.
picture.
Okay, hold on 1 second. It just stopped sharing. My bad. It'll come back up in a second. Thank you for letting me know that. What about now? We good?
Yes, we can see it.
Okay. So for carbanions, this is obviously methyl, and then this would be primary. Just leave it. And then this is secondary. And tertiary. Let me go back over here. I think I left off a hydrogen. Yep. All right. So for carbanions, it's the opposite. It is the less substituted anions that are more stable. So this is most stable. And this is least stable. But the reasoning behind why one is more stable than the other is the same. So let's take the let's take the carbocation, the tertiary carbocation. So it is here, CH3, 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 and that's positive. Anytime you see a carbon with a positive charge, that means it has an empty orbital somewhere, right? So when for the tertiary carbocation, these carbon bonds adjacent to it, there's a small dipole for each one of them going towards that plus charge. Everybody remembers dipoles, yes, or at least most of you should remember, right? The
Yeah.
plus charge is, and that carbon is sp2 hybridized, which we haven't talked. We talked about hybridization, but I didn't talk about it in terms of electronegativity. But I'm not going to dump that in right now. I'll find another place to put that. So the plus charge is an electron. It's electron poor, so it's sucking electrons from those carbon-carbon single bonds, right? So that situation is called, it's a term we use, called hyperconjugation. And that is so that's stabilizing a carbocation with electron density from carbon-carbon single bonds. Right, so you're stabilizing a carbocation with electron density from these carbon-carbon single bonds, which are more electron rich. So that tertiary carbocation is the most stable because it has the most groups around it that can funnel electron density towards that plus charge. All right. By the same token, the anion is the least stable. The tertiary anion is the least stable because of the same reason. It has a charge, it has electrons, it's electron rich. And if you got all of these carbon-carbon single bonds around it, right? This atom is already electron rich. And so more putting those electron rich bonds around it is going to destabilize the charge. Right? So they stabilize positive charges, but the negative charge becomes destabilized because it's just too much electron density around that. And you know that electrons from CHEM, that electrons repel each other, right? They don't come to each other. They repel one another. They're not attracted to one another. All right. Are we okay with that? Any questions about that?
I have a question.
Come on.
So you're basically saying that tertiary is destabilizing, but it's also most stable?
It depends, but tertiary what though? So that's the caveat. If it's a tertiary cation, then it's the most stable of all the cations. If it's a tertiary anion, which I should have written out over here, and I can do it now, and it's the least stable because of the same reason, like the substitution. So the more groups you have around a cation, the better. The more groups you have around an anion, it's not so good. It's more. It actually makes that anion worse, if that makes sense. Because if it's already electron rich, it doesn't want more electrons around it. That's the reason. But the cation is electron poor, so it wants electrons around it to help stabilize it.
Is that also what you put at the top right corner as well? Like right next to the cation where it says
On
tertiary
this
is
sheet or on
most
the other
stable.
sheet?
This one right there
Yeah,
on the
yeah,
right
yeah.
side.
So yes, same thing. So this is, notice what's around it. Look what's around that carbon, right? Nothing but hydrogens. So that's a methyl anion, and it's the most stable of all the anions because it's the least substituted. Right? It doesn't have any bonds to carbon. And the minute you start adding bonds to carbon, you start destabilizing that charge, that negative charge, if that makes sense.
Yes.
It's kind of like, and I hate to say this, but I've been saying it forever, so I'm gonna say it. It's kind of like a person that's very independent versus a person that's very needy, if that makes sense. An independent person doesn't need a big crowd around them to feel comfortable. A needy person may need a lot of people, a lot of friends around them to help them feel comfortable. Are you following that? And so it's the same way with cations and anions. Cations, because they are electron poor and deficient, they need a lot of groups around them to help them be stable. Anions, on the other hand, are the opposite. Because they already have electrons and they are electron rich and they have a charge, they don't need a lot of groups around them. Actually, the more groups you bring around, the less stable the situation becomes, if that makes sense. All right, so let's go back to our example. So what type of cation is this CH2? Is it methyl? It's not methyl because it would just be CH2 by itself, right? Or CH3 by itself. Is it primary? Is it secondary? Is it tertiary? What is it?
Primary.
They're both primary. Good, excellent. Now, here's the question. If you look at the primary cation on the right, you have a double bond here, but are they able to do resonance?
No.
No.
No resonance. Why? You're both right. Tell me why you can't do resonance in that situation.
The double bond is adjacent to the cation.
The double bond is too far away, isn't it? So no resonance. That's good. Excellent. What about over here? And this is primary. This is also primary, but what's the difference?
How close the double bond?
The double bond is adjacent to it, so now it's allylic. And if it's allylic, what can it do that the other one cannot do?
Resonance.
It can do resonance. This is an allylic cation. This is one of our patterns that we saw when we first started studying this. So we could take this double bond and shift it over to here and stabilize that plus charge. Otherwise, it's just simply a primary cation just hanging out, and that's bad, right? That's one of your worst carbocations is the primary. But over here, since it's even though it's primary, it's also allylic. So I can draw a resonance form. I'm gonna squeeze it in here, even though I know it's gonna be bad. Just bear with me. I'll have a resonance form that looks like this. And now the plus charge is here, and the CH2 is here. And I can go and I can interconvert between those resonance forms. So the question now, let's go back. Which ion is more stable? The one that's unable to do resonance or the one that can do resonance?
One that can.
Yes, resonance is a way of stabilizing charges. It's a way of delocalizing charges, delocalizing electrons, delocalizing electron density, right? So this is more stable. This is less stable. And the other one is more stable. Come on, Russell. We're gonna say that this is resonance stabilized. Resonance stabilized. All right. Questions about that? I know we went all the way around the world to get to that, but that was a great place to talk about cation stability, right? Great place to talk about it. All right, let's go to E. Let's do E. Let me see if I'm gonna be quiet on E. I'm gonna see if y'all can figure this out with a clue. So here's your clue.
Can you hear me?
Yeah, I can hear you just fine. Go ahead.
So I would say the first one will be more stable because of the lone pairs with nitrogen.
Okay. Okay. What can those lone pairs do? Is this one of our patterns that we've seen? And isn't that a diatomic unit? I agree with you 100%. You're absolutely right. But what can I do with that lone pair in reference to a resonance form? Can I do a resonance form with it?
Yes.
I can. I can move it here, can I? Not there. I can move it here. Is that right?
Yes.
And the resonance form, don't have room to draw it. I'll draw it over here. The resonance form would look like this. But now this is positive, right? So what I've done in essence is I have I've shared that charge over two atoms, right? And that would be considered a secondary cation, but because I can do resonance, I can stabilize it. What about here? What type of cation is this one? How many bonds to carbon does it have? It's bonded to 3 carbons, is that right? Can y'all see that? The 3 carbons
Yeah.
attached to that? Let me change the color on that one. Right, so that carbon is what? What's the bond order? Primary, secondary, tertiary, what is it?
Tertiary.
Tertiary. Is that generally a stable cation based on what we just discussed?
No.
Let's go back and look at it.
I thought it was yes.
Well, actually,
Yes.
the chart is over here. Tertiary is, well, I didn't put the stability trend on this, so we can go back. Tertiary is the most stable out of all your carbocations. But when you compare it to here, where you can actually take that plus charge and put it out like a fire, you can give those electrons on nitrogen to it and actually neutralize the charge altogether. That's gonna, this structure on the left is gonna be more stable. The tertiary is stable. Don't get me wrong. It's a very stable carbocation, but the fact that you can do resonance on the left and actually fully neutralize that charge, that molecule is going to be the most stable of the two, or the more stable of the two. All right. Questions about that, or about either one of these examples? Right, I can actually share that charge between two atoms as opposed to drawing electron density from the atoms around. In the example on the right, it's just pulling the electron density from the bonds, but the charge itself is still stuck on that one atom. Whereas the example on the left with the nitrogen, I can actually take the charge and put it on nitrogen and share it between those two atoms, and that's more stabilizing. All right. Any questions about any of those examples? All right, we got about I actually got to stop a little early, but we got about 7 minutes left. So let's go to, wish I could flip this page around. Let's go to, let's take this one. I'm just gonna cut it and then paste it on a new page. I think I can turn it if I add a new page. All right. So let's look at B. So it's given, B is given to us as our starting structure. And it says label each species as an isomer, which I'll explain in a second, or a resonant structure, or neither, right? So 4, we can go ahead and rule out 4. 4 is, it can't be either. It's not a resonant structure. It's not a isomer. Let's look at 1. And first, before we do that, let's draw all the resonance forms of B. And that'll save us a lot of grief as far as identifying what's resonance and what's an isomer, and it'll give an opportunity to explain isomerism, right? So what would you do with B? Here's the pattern. It's an allylic cation. What would your first resonance form look like? Anybody? What would you do?
You move the pi bombs at like the top left, and then put that right there, and then that would have a positive charge on the left, I think.
So you'll put the plus charge here,
right?
And then put the double bond here, and then this double bond didn't move. Is that right?
Yeah, that one doesn't move.
Okay, hold on one second. I got to take this call. Hello? Are you at the gate? Okay, so when you come through the security guard, come past him, make a left, make that first left. And then come down, and you're going to see a green crane, make a right into that parking lot. Okay, thank you. Bye. Sorry. All right. So yeah, can we do that? Where's our next resonance form? I'm gonna have to edit that out, by the way. I ain't gonna leave that on YouTube. Where's my next resonance form? Can I do another resonance form?
Yes, you remove the pi bond on the bottom towards the left.
Right here?
Yes, sir. And then the plus charge will be at the bottom.
Good, excellent. Okay, so that's that, and that. Is that right? Oh, I'm missing a methyl group. Y'all ain't even tell me. All right. Is that right? So what is 2? Let's look at 2. Is 2 a resonance form? It matches one of these, doesn't it?
Yes.
What about so 2 matches here, doesn't it? The other resonance form, do we see that one anywhere? Is it 1 or 3?
No, it's not.
It's neither, okay? But if you look at 1 and 3, they have the exact same structure, don't they? They got the same structure. The bonds and the charges are in different places. So 1 and 3 are what we call constitutional isomers. And this is a long draw. I don't want to get too deep in the weeds on isomerism because that's a long and arduous discussion because it's just so meticulous to get into it, but we won't get into all of it today. So 1 and 3 are what we call constitutional isomers. They have the exact same molecular formula. But they have different structures. Right, so you can see here, the structures are different in that the double bonds in 1 and 3, and the charges are in different places. So the structures are not the same, right? So 1 and 3 would be considered constitutional isomers of B and not resonance forms.
Okay, I get 1 is not a resonance form, but why not 3?
Look at where the methyl groups are on 3. We did that. We have that one. Hold up. Did I put this double bond in the wrong place? I believe I did. That should have still been here. Does that match 3? It still doesn't match it though, right? That here, that here. So neither one of those still, they don't match any of the resonance forms. So they'll still be considered constitutional isomers. Because if you look at 3, look at the methyl groups on B, everything is oriented the same way, but the bonds are in totally different places. Even if you looked at the fact that the bonds here and here are too far apart. Can you see that? If you go back here, you see how we talked about this briefly, like conjugation right here. So double, single, double. But over here, you don't see that in 3. And you don't see it in 4 for sure. I mean, you see it in B and in 1, but where that plus charge is in 1, it doesn't match. It doesn't match B or any of the resonance forms. So it has to be an isomer, if that makes sense. That's why we drew the resonance forms first, so we could rule out what was and what wasn't, and then go back and discuss the difference in an isomer and a resonance form. Did that answer your question?
Yes.
Okay. All right, we actually got to stop. It's 10:48. So I'm gonna stop here. We'll pick up. We're gonna do a half of resonance on Wednesday, and then we're gonna start that second module, which is dealing with pKa and acidity. So it'll be a different handout, and when I send the announcement out, I'll tell you which handout to get and all that stuff. So, any questions before we log out?
I have a question. Can I ask
Go
after
ahead.
class?